Good day, ladies and gentlemen. I'm back again. Today, I want us to do mechanical energy and the principle of conservation of mechanical energy. The lesson is presented by me, Mvakade KF. Okay, let's start. Mechanical energy. What is mechanical energy? Is the sum of the gravitational potential energy and kinetic energy. It is the sum. So mechanical energy is equals to EP plus EK, where EP is the gravitational potential energy, EK is the kinetic energy. So we can further write this as Emec equals to mgh plus half mv squared, where mgh is the formula for EP and EK is half mv squared. So we did the potential energy and the kinetic energy in the previous lessons. So what is the principle of conservation of mechanical energy? The principle of conservation of mechanical energy total mechanical energy in an isolated system remains constant. An isolated system is when the resultant or net external forces acting on the system is zero, is equal to zero. So this simply means we can just say if maybe there is the absence of in the absence of non-conservative forces. So we can write the principle of conservation of mechanical energy as follows: Emec initial equals to Emec final, where Emec initial is EP plus EK initial is equals to EP plus EK final. Okay, now there are some things that we have to note there when this, especially when coming to solve problems using the principle of conservation of mechanical energy. So when the object is given an initial velocity to move upward, the kinetic energy of the object is converted into gravitational potential energy. As we all know, if an object is projected upward, its velocity will decrease. So as the velocity decreases, the kinetic energy decreases. So the kinetic energy is being converted into gravitational potential energy. When the object is dropped or given an initial velocity to move downward, the gravitational potential energy is converted into kinetic energy. This also applies like here. When the object is dropped, when it is dropped, you know that the initial velocity where it is dropped it's zero, but as it moves down, its velocity increases, but its gravitational potential energy decreases. So the gravitational potential energy is converted into kinetic energy. When do we apply the principle of conservation of mechanical energy? Apply the principle of conservation of mechanical energy when non-conservative forces are okay. So let's do an example where we solve problems using the principle of conservation of mechanical energy. What do you have? A skier of mass 80 kg starts from rest at A. The downslope is curved and frictionless. Refer to the figure below. Okay, we have A, B, C. This is the ground. This is the ground. Okay. Now, from A, we are asked to describe the energy changes that take place. Describe the energy changes that take place as the skier moves from A to C. From A to C, the movement is downward. So gravitational potential energy is converted into kinetic energy. That is the what you call energy changes. Now, gravitational potential energy is converted into kinetic energy. Okay, so we have what? B. For B, we are asked to calculate the potential energy of the skier at B. At B here. So EP at B, mgh. Okay, where m is the mass of the skier, it's 80 into 9,8. What is the height from the ground? It is 20 meters. 20 meters. Okay, so this go 80 times 9, 9,8 times 20. No, times 20. So it is 15,680 joules. So this is the gravitational potential energy at B. Okay, C, we are asked to calculate the speed of the skier at C. And now we can use what to call the principle of conservation of mechanical energy. Okay, so we can simply say EP plus EK when initial is equal to EP plus EK final. Okay, so what do you have here? We're going to have mgh initial plus half mvi squared, which is I for initial, is equals to mghf for final plus half mvf squared for final. Okay, so we are told that from the statement, we are told that the skier of mass starts from rest. From rest, we know that the velocity is equal to 0. But what is the height above the ground from A? It is 50 meters. So we're going to have 89,8 multiplied by 50 plus half into what is the mass? 80. Rest initial is from rest 0 squared, which is equal to final. Okay, at C, here at C, we know the height is 0. So this is going to be 89,8 okay, plus half 80 VF squared. That's what we are looking for. So what do you have here? We're going to have 39,200 plus, which is 0. It's equal to, here it's 0, and plus half of 80, it's 40 VF squared. Okay, so we're going to have 39,200 is equals to 40 VF squared. So we divide both sides by 40, divide by 40, this cancels that. Okay, so divide by 40, we have 980 is equals to Vf squared. So we introduce square root on both sides. We introduce square root on both sides, and now Vf is going to be equal to answer 1 over 2 square root, going to be 31.30 meters per second. Okay, so I applied what you call the principle of conservation of mechanical energy to solve this problem, because I was told that this is frictionless and that it starts from rest. So there is no applied force, there is no tension force, and there is no friction. So the non-conservative forces are absent in this in this case. So hence I can use the principle of conservation of mechanical energy. I hope you understand, good people. That's it from me. Thank you.